Okay, nice to hear from you. Today we have a survey in the very beginning to get me know what I know and what I don't know about you. And after completing the survey, we will try to start on the base of what you have talked to me. And so we have not much people here. I hope more people will vote, and so we will adjust the level of lecture to them. But in general, today we will talk about what is adversarial attack and what are the challenges for creating adversarial attacks if we are working not with usual image data, which is like a typical scenario when we're thinking about application on neural network, but instead we try to see if what happens when we move to a sequential word and what kind of challenges we want to address and so on. Okay, so I'm happy that you have voted, most of you, and that almost all of you know what's adversarial attack. So I think we will briefly recap what we have did before when we are trying to construct deep neural networks and then slightly move in a slow pace to adversarial attacks and then move to sequential data adversarial attacks. So as all of you know, we have like this typical scenario of usage of deep learning model. When we start with image as an input, we pass it through a learned neural network, and we have an answer by a neural network. For example, we can say that it's a panda with quite high confidence. This is how our neural networks works. And so we can say that if we have this like classic example for a challenge for image recognition, like ImageNet with about 1 million images and about 1,000 object categories, we can say that, and we want to make 5 assumptions, and so that one of these assumptions is right, then we can try to see what the accuracy of these top 5 assumptions. And right now, modern deep neural networks have much lower error rates than humans. And if you look to the side papers we got, we can see even more amazing numbers here. I suppose it's something like 1.5%. Now, maybe you can correct me, but okay, you can see that still we see that now humans are not as good at image recognition as machines. But is it right that these deep neural networks are good and so we can replace humans everywhere? And so we don't need them anymore? The answer is kind of yes, but they can become very strange things when we are talking about how we apply adversarial attacks. And so, for example, maybe the most common example is an adversarial attack. And what is kind of how can we make an deep learning model useless? So we have this usual pipeline for construction of a deep learning model. So we have like this training data. We trained the model using this training data using some kind of algorithms and the model, and then we have a model that can take an image as an input and have something as an output. And so how can we make this system, this scheme, this workflow doesn't work? I will start with less popular approach. It's about that we can poison training data with some carefully selected training examples. And actually, this kind of similar of what one of your teams is doing right now during the project when we try to somehow include some additional information in the message, and so it would be hidden from other people. But at a simpler level, we just add some specific examples to the training data. And after this, when we train the model, we have some very strange model with some peculiarities from what we can say that this model is not very good. Another, maybe the most popular option is like 99% of the literature, is that we can slightly change the input And so we can fool the model because after the small changes, we apply the same model, but we have another output. And this output is completely different in terms of accuracy and in terms of what we expect for this particular image. And we can say that in this pretty basic scenario, we can have one more step, and we can have this adversarial change of input to our neural network at a physical level. So we can say that we put a marker on the stop sign, which is in a yellow cycle. And now for a neural network, it is not a stop sign, but rather a speed limit 65 sign. And it works in many scenarios like this in a physical world. But right now we focus mostly on adversarial attacks when we have full access to the model, or at least to the input of this model. And the most popular and the first result in this area is a famous paper by Sigrid, I suppose the family is pronounced something like this. So in this case, we say that we have like an input image, and we want our model to be mistaken to be fooled by this image. So we have create some noise, design what noise we should add to an image to get another image. As you can see, for human, there are both images of panda. But after putting this new image as input to our neural network, then we have very high confidence that this is not a panda, but it's a gibbon with very high confidence. I think that almost all of you saw this figure and understand what's going on. But okay, if you have questions, you are welcome, and I would like to answer them. If it's the first time you see this kind of workflow. Also not, okay, returning to the lecture, we can kind of say that's not something unique, that adversarial attacks exist also, okay, not only on deep neural networks, but on our neural networks too. And we can, for example, see that the image at the left part of the slide is moving, but actually it's like a static figure. And okay, it's kind of strange that we can see this kind of behavior. We can also see an illusion at the right side of the slide. There we know, at least we can try to check it with a ruler, that there are 6 parallel lines, and these lines, not curves, but our brain is tricked, and we can imagine that this central lines is different from like straight lines. They have some curvature in the middle. And so, okay, we can say that for human brains, we also can create adversarial attacks. Moreover, application of this kind of tricking of models is not limited to only images. We can do the similar thing with audio signal. We can say that, okay, now we add some specifically crafted noise to the audio signal, and now the voice recognition system works, okay, completely differently. It's no longer how are you phrase here, but despite the tiny size of the change, we see that now it opens the door. Kind of very strange, but it's similar to images. Also, okay, for physical world is also interesting, and I suppose I talked a bit, but let's give 2 more examples on how does it work. For example, for the stop sign, we can see that now we put some stickers on it, and now we fool our dependent model. Another example is this strange turtle, and when you kind of print this turtle using a 3D printer, and you try to rotate it, most of the time you recognize this turtle as a rifle. So it's when we know what to do, we can trick the learning model and turn a turtle into a rifle or vice versa. Also, we can say that we don't need much to do this kind of attack, which gives us some hope when we will move to adversarial attacks for sequential data. But okay, in this slide, you can see that we change only 1 pixel, for example, here and here. And after application of this change, we see that the label of the figure is completely different. It's no longer automobile, it's a track. The same magic happens to this button that suddenly is a deer for our neural network, and so on. So it's kind of easy to do something like this due to very rich number of images. Also, another important note about adversarial tags is that sometimes we can create universal adversarial tags. In this case, we are no longer interested in designing the perturbation of a particular image, and we are interested, can we find a pattern that tricks model for multiple images. So we add the same transformation to each image, and we get wrong labels for almost all modified images. And the answer is that yes, we can do something like this. This universal adversarial tags. In this case, we kind of add similar transformation modification to each image, and after applying this modification, we see that okay, images are pretty much the same. Okay, maybe it's you can distinguish that they are different, but okay, that's still a flagpole for a human eye. But after application of this transformation, most of images are classified as a Labrador, and kind of okay, strange thing, but it's pretty easy to construct such attacks. But what is the approach behind the most successful and the most powerful attack? Okay, suppose that we have an access to the internal side of our deep learning model. So we can say that we know all the parameters of this deep learning model, and we can calculate the derivative of the loss function j with respect to the pair of input and output. And okay, sorry, okay, yeah, we can. 1 minute, please. I have some problems with my pencil. Okay, let's do it one more time. We say that we have this loss function, and we calculate the derivative of this loss function with respect to input here. Input in this case is O, so O is our image. And so we move in the right direction according to this derivative of loss function. So it's equivalent to trying to modify the label of the data, the probability that the object belongs to the target class with maximum speed. Okay, moving into the direction of the steepest descent. And so we add this derivative to our initial image. So this is our O. This is our modification after multiplication by this step size epsilon, which can be quite small. Then we obtain the resulting image, and voila, we fool our deep learning model, and we are no longer expect this is shared soup. Instead, we classify it as a terrier. And using this coefficient epsilon, we can vary how different these two images is. For example, we can say that we want to limit our perturbations, and if we say that epsilon, for example, equals to 0.01, we can say that the L0 norm, yes, the maximum difference between each part of an image is okay, is equals to this epsilon, because we not only take the gradients, but we use a sign of this gradient. So it's after this application, we have +1 or -1, and after multiplication by epsilon, we have plus 0.01 or minus 0.01. And after it, we can say that our perturbations are small, and we are mostly happy with the result. And actually, in this problem statement, we don't need something more complex. We can do it in this way. It just works. We can do it even better if we take not one step, but a number of steps in this space of input images. So we say start with initial image. This is our, okay, we have it here. So it's our initialization. And then we try to move by the gradient steps in the space of images, and we make several updates, 3 capital updates to our image. So we start with 0, we with O0 with title, then we after first step at O first, and so on until we reach the final modification. And by controlling this alpha value, we can say that if we have this alpha t equals to epsilon, then we can see that the maximum difference between each two pixels in the initial image O and the image O tau t is no larger than this epsilon value. So we have easy approach, and we can easily control how much perturbation do we add to an image. This is kind of state of the art, and I suppose that okay, it would be very strange if someone can invent something that significantly outperforms this kind of approach. But to add to this discussion, we not always have access to white box adversarial attacks, white box neural networks. Instead, sometimes we need to create adversarial examples for black box models. In this case, we don't have access to the gradients. We can only query the model in the following way. We have like some input, and we have a label of this input. So maybe like it kind of belong to the class label from 1 or from 0 to maybe okay 10,000 for ImageNet. And so each time we have these queries, and we can try to use this mechanic to create adversarial examples here. And what can we do is an example of an approach on a black box adversarial attacks when we have access only to the labels produced by this input X. And so we say that we start with from some image. We try to move in the direction of the original image. A starting image is from different class than the original one. So we somehow, if we move not very fast, we are still in the part of space of images where we have a different label for the current image and the original image. So it's adversarial example. What we need to do, we need to move as close as possible to this original image. What we are doing after application of random perturbation to our image at some time step. And actually in this algorithm, bounded black box adversarial attack, we are doing this in 2 steps. We start with orthonormal step, it's illustrated here, orthonormal to the connection between the original image and the true image, is the first part. And the second part, we try to kind of move in a random direction, no, not in random, move in a direction to our image to get closer to it. So in the end, we have this distance smaller than the distance between our initial image, our initial adversarial image. And also, okay, we had some small perturbations, which is not depicted here, but it does not matter much. So kind of start with something like this, very small random perturbations. Then we add this one orthogonal step, then one step towards the target image. And it works also pretty fine, except that we need much more steps to reach good looking adversarial examples. For example, here is our original image, and we want to create an adversarial image, so it has different label from the original one, but it's very close in terms of some kind of norm. So we start with this image of a dog, and gradually we are moving closer to the initial image. And so this is what we have after about 600 calls to the target model. And after all, after like 400,000 calls to the target model, we see that we have a kitten that our model thinks is not a kitten. And we can try to do to repeat this procedure for example, some random noise. And in the end, we have this caterpillar, which is, okay, not caterpillar, okay, don't know what's the name of this insect, but whatever, you can see that these two images are very close to each other, but we still need very large number of calls. So black box is kind of possible, but it's kind of like genetic approach to search or quasi-random approach to searching the adversarial image. So it takes many steps to get the good image. There are some more recent algorithms because this guy was proposed in 2017. And there, for example, another approach that the authors call Simba proposed like in 2019. Basically, we also like kind of randomly move in the space of images, trying to create an image that is close to the initial one, but has a different level. And okay, here is the whole algorithm in this paper. So we have kind of these probabilities. So we don't have labels, but rather we have probabilities for a label. And we want to move into the direction of decreasing this probability. And what we are doing, we select this, okay, we have this initial point. We select Q, okay, we have this delta initialized as 0. And so basically we have this X, and we add this random perturbation Q multiplied by step size alpha. So we have another image, and we have the probability for initial image and probability for this modified image. And so we say that now we want to check if we have a better move, a better image than it was before. And so we compare these two probabilities, and if we improve over what we have before, we say that we modify our delta, and now it includes this step alpha Q. And so we continue. Okay, we continue until we are happy about the final result. So it's kind of, we add another step and hope that this step will improve our scores and so on. So if we have additional information, we can do much better. If we have access to the probabilities produced by a model, we can, instead of like blindly looking for an area where we know that we are okay, that we have a class different from what we had before, but okay, it's kind of tricky procedure. In this case, it's much faster. You can look the details in this paper, but okay, I don't want to spend more time on this. What we can say in the end of this section, or at least we are very close to it, we say that if we have access to these derivatives, and if we have a very rich space of modification, so we kind of change what value of each pixel S can move to black to white, or even slightly alter, so like from 2038 to 2020, and so on. So we have like very large number of degrees of freedom, and we walk around the space, and then we have an adversarial example. Okay, these two properties I already told you like multiple times. So if we have the derivatives, it's pretty easy problem. Also, it's important to note that we not only work in the direction of attacking these models, but we also trying to improve the resistance of this model to attacks, which we call, and not only we, but okay, general scientists, and defense strategies. Maybe the three main defense strategies is here. Okay, maybe the simplest one and the most close to the business understanding of the problem is gradient masking. We try to somehow make gradients useless. In this case, we are no longer can apply FGSM, fast gradient sign method, when we know the direction to go and we go along the direction, and we have a good solution after one or similar iterations. Also, we have like two most sophisticated strategies, which we call adversarial training and discriminator training. And discriminator training is that we train a separate neural network, and this network solves a classification problem. It tries to distinguish real images from fake images created by this adversarial attack. And so in this case, if you have a successful discriminator, as a separate neural network, and we kind of fault this adversarial attack and say that if this separate network is sure this is a fake, we can just say that we refuse to classify the image and say that maybe something wrong with it, maybe we can pass it for a human examination in the end. And also it's important to mention the last strategy, adversarial training. In this case, we, in a simplest scenario, we just add these adversarial examples, these correct labels to a training sample. So let's imagine that we have like this initial training sample and we applied an attack. And now we have these additional images that correspond to the attack, but the label of these images is different from what is expected. So it's kind of this pandas classified as ribbons or like gooses classified by as trains. In this case, we put the right label, which we know that we have this like two close images. So we just transfer the label to, it should be still panda, we set to our neural network. So we retrain our network using this expanded training sample. And in this way, we learn that these augmentations made by an attack is mitigated, and now we have a stronger model that can resist this type of attack. So it's what we call adversarial training. I will give another algorithm that also doing adversarial training. That do it in a more sophisticated way. We don't need to retrain the model, and this is what we have in NeurIPS 2019. In this case, we kind of say that we want that if we have small perturbations generated by an adversarial attack, then after application of this small perturbation, we still have the right classification. So we have this delta, which means what kind of modifications we apply to our image. And we learn parameters, these are parameters of our neural network data, and parameters. And we take the gradient of the loss function given the modified input, modified by delta, the true labels, and the parameters. So we can make this step for update of parameters data. Also, we can update this delta values. What are the most promising adversarial step? So we kind of say that we apply delta and add delta with this signs of gradients with respect to input. So basically we are doing something like FGSM approach when we slightly modify the input and find the modification that has the biggest effect on the result for a model. Okay, then we for sure can clip this delta, so it's not very large, but in this way, we kind of increase robustness of neural network to adversarial attacks. There are a lot more approaches, but I would like to stop at this example and ask, do you have any questions right now about what I have told? Because we kind of at the end of the first part of my talk. Okay, you can write plus sign if you understand everything and think about some questions to me if you are worried about some part of it. Kirill, maybe you have some specific question so I can help you because, okay, there is not a lot of personal communication, unfortunately, in this course. Maybe you can kind of, maybe it can be very basic questions. It's okay, still okay, because it's important topic. And okay, after this part, we will have a bit more advanced topic when we're trying to apply the similar adversarial attacks to a simpler, or okay, not simpler, but more complex models for the processing of sequential data. Oh, whoa. Kirill, do you understand now what is an adversarial attack? Okay, let's do it like this. Okay. Do you understand what is a GSM approach? Okay, you can try to describe it by voice here if you have access to a microphone. So we can discuss, okay, what we are doing wrong and maybe what we can improve into your understanding. So other also can discuss it and maybe help Kirill with understanding on what's going on in this. Kirill, can you please turn on your microphone and describe what is? Okay, I understand. Okay, maybe someone can help Kirill and understand and explain one more time what is FGSM attack, so I can be sure that everything is okay. Pavel Burnashov, can you try to explain what FGSM is?
Well, during FGSM attack, we tried to add some noise to input features so that classifier will misclassify the true label.
Okay, and how exactly do we add this FGSM noise? How do we collect the noise in this case?
Well, for example, the noise can be the gradient of the loss function.
With respect to what?
With respect to true input features.
Yes, exactly. So we kind of do it. And why do we need, okay, when we are thinking about FGSM, we say that we modify our input with epsilon with multiplied by the gradient of the loss function of input and y. Why do we need this epsilon here to get this adversarial example? Okay, maybe someone else can help. How?
Well, maybe to control the difference between the input and modified features.
Okay, yeah, good. And also what I miss in this formula, what I don't have, that actual FGSM have. Yes, exactly. So we have additional sigen. So after application of this sigen function, we say that now all these derivatives is either +1 or -1. So we kind of, for each pixel in the image, we say that for some pixels we want to increase the color, for other pixels we want to decrease the color. So it's like in what direction we want to modify each pixel in an image. And so by multiplying by epsilon, we have these changes, not +1, -1, but rather plus epsilon and minus epsilon. But it is still according to the direction of the initial derivative of the loss function with respect to input. And so we hope that after applying this crafted perturbation, our O prime is very close to O, actually is close, is equals to epsilon, but the label of this O prime is different. We at least hope so because of this targeted perturbation. We tried to get the maximum of what we can do right now. Yeah. And also another question for your self-control. What can we do when we are trying to do black box adversarial attack, and we have another student to explain this to us. Maybe I can ask Daniil Moskovsky to try to explain what's going on when we don't have access to the gradients and to the internal part of a deep neural network. Daniel, can you provide an example of a black box adversarial attack?
I guess in black box adversarial attack, we don't have access to the model at all. We only can use the result that the model provides us.
Okay, and how can we attack in this scenario? Does there exist any approach to do this black box adversarial attacks? Can you name one of you?
I forgot how it was called, like a couple of
Okay,
slides ago.
you can describe the idea. How can we modify the image? So we have access only to the output of the neural network. So we kind of say that we have image here. We have this.
We like iteratively change the parts of the image. It was a slide with the changes from from the dog to the kitten. So like we make small change and assess the output that the model our model gives, and finally we get the almost different picture but the same result. Like,
Okay, vice versa, but okay, yes. So we have similar figures, but the result, the classification result is quite different. And we try to move from this initial image to this adversarial one by like more or less random walk, maybe with some targeted perturbations, but actually very close to like discrete optimization because we don't have access to the gradients of the target function. We can only say that for this image it's dog, for this image it's cat, and we somehow try to find a closer image as specified as dog2. But okay, we know only this kind of optimization of a discrete function, quite hard, and so on. Okay, so let's go on and try to move further and try to move our actual topic here for today because we are still at the course of sequential data processing. And right now we will try to apply this magic way to corrupt and to fool models in another part when we have like a sequence. And okay, as you know, these models are very powerful. Okay, I think I will miss the slide at least, but we are still kind of interested in can we create adversarial examples. Okay, as most of the work in this area is devoted to natural language processing, we say that, for example, we can try to uh, break to fool the chatbots so they answer something different and kind of strange and to find some weakness in this chatbots. And also we can try to make home assistants to think about something different. So they do other things, like they're buying something, and it's kind of fraud. Maybe not a very realistic scenario this day, but at least we can try. Or maybe we are trying to produce a realistic spam images that can pass spam filter that are also constructed using machine learning. Or we can try to produce fake news that are looking like real news, but it kind of has some adversariality in the heart of these fake news. Also, when we are moving from NLP data, there is also a lot of interesting examples of what we can try to do with credit scoring or fraud detection. And for example, we can say that, okay, we have this series of money transactions, and we know like the credit rating for a customer, and like it's not very good. We can say that it we return the credits with probability 0.1, so it's kind of bad customer, and we should not give credit to this customer. But okay, can we try adversarial attack this model? Can we add some kind of transactions, for example, to buy a bread or go to an ATM to collect some sum? So after application of a model, we are pretty sure that this customer is good, and so we can give him some credit. So are this type of attacks possible? Also, we can ask the same question about fraud detection. So I suppose all of you know that sometimes, okay, malicious people try to steal money from normal people, and they obtain access to the credit cards and try to buy something or try to go to ATM and like extract money from the card and go away with this money. And in this case, it's also interesting, do there exist approaches that can be look natural, but in the result, it will cost something for healthy people. And also this question interesting not only in terms of attacks, because I think that we all are on the good side, but also what we can do about increasing the quality of our models so they can be tricked in this way. How can we increase the robustness of this model, and what kind of model should we select to increase the defense from adversarial attacks? And last example as a slide is about fraud detection medical insurance. Suppose a patient came to a hospital and then came to a specific doctor, and a doctor says that this patient should go to this, and this procedure, a lot of them, and actually doctors try to increase number of procedures, especially if an insurance company pays the hospital for processing of these patients and for each particular procedure. And this case, it kind of not very good for insurance companies because they lose money, and I suppose it's not a very good thing for all of us because it's kind of fraudulent case. So there is two similar questions. Can doctors manage to create a strategy that prevents them from identification? So maybe there are some procedures that definitely show that this doctor is on the fair side and he doesn't try to increase the profits of hospital by decreasing the profit of an insurance company. And so again, from the attack problem statement, we go to defense problem statement. How can we make models more robust to this kind of behavior and identify this malicious behavior using what we have in our pocket for adversarial defenses? Okay, so we have this diverse applied problem statements, but generally all of them are connected to the same idea. How can we create adversarial attacks on sequential data models, and how can we defend from them? Actually, for images, it was pretty easy to create adversarial attacks because we have a kind of simple approach to create these perturbations. We take the gradients in the space of images, we add this gradient, and right now we have, instead of duck, echoes. Can we do in the similar way for sequential data processing? And the answer is no, because of not even one, but many reasons. At first, it's very hard to add very small numbers because we can change only one word. We can say, okay, we have this Socrates. We can change it like to very close to Socrates, something. We should change one word to another. So it's harder to include the noise that can be spotted and don't change the semantics of the sentence if you're talking about natural language processing data. Also, we don't have backpropagation because in this case, we can calculate this guy because our input is not a continuous, doesn't lie in the continuous space of images. It's rather lie in this discrete space of words. So we have like this words from a dictionary at first position, second, and so on. So we actually have discrete data. And it's kind of problematic because we can't directly use gradients. Also, it's interesting to see if we can do targeted perturbations. For example, it's a question about what if we can only add a transaction. So it's kind of we have access to the history of transactions of the client, and we want him to look nicer to a bank. And in this case, we can change the path because the bank owns the data, and definitely we can go to past with a time machine and buy something in the past to change the credit score. Instead, we can add something in the end to make attacks better. And so, okay, sorry for this confusion. Let's go back to what. And so we will try to cover both these issues and cover the state of the art, what's now considered a good approach to adversarial attack if we are working with sequence data. Okay, here is a little overview. So, okay, actually what we will not consider is kind of very specific NLP-based approaches. For example, we can replace one synonym from another on the basis of curated list of synonyms. Yeah, we can do this, but I suppose it's kind of not interesting. Every one of you, I think, can manage to create and to apply in 1 or 2 days. But instead, we're interested in a more general approaches that can be as well applied to, for example, transaction data or the spending on insurance data. And basically, these two approaches are, okay, these approaches lie in 2 fields. The first one, if you try to select a token to replace, and for this particular token, we are trying the one that corrupts the model score the most. And also we try to move from this bad promise statement to good promise statement and try to move to an embedded space. And in this embedded space, we will try to apply an approach similar to FDSM. Okay, I'm sorry, I'm doing something stupid, but we are back on the track now. And as an example of this token replacement strategy, I will talk to you about hot flip approach to adversarial attacks. In this case, we have this white box or a surrogate to attack. Surrogate is something similar in terms of the data the model was trained on, but maybe something different from our original model, because usually if you are a malicious user, you don't have access to the initial model. To try to attack, maybe you can have some smaller data set, but not yet. And so we can say that, okay, we have 2 types, non-targeted, targeted, but doesn't make much difference, almost all the case. Not targeted is that we just want our class to be different from what it initially was. For example, if we have a panda, we want the modified image to be classified in a different way than panda. This is not targeted. And targeted attack is when modified image, we want it to be not a panda, but a specific class, for example, a horse. I don't know why you want to change panda to a horse, but whatever. Maybe, okay. And so in this scenario, we try to replace one part of the sequence. So we have like this sequence of tokens, X to, I don't know, okay, it will be T. This is our X in general. And each xi is a token from dictionary. Then we can try to calculate the loss function with respect to each component, and in which direction we do a replacement. In this case, we use this kind of one-hot encoding for vectors. So this guy has the length of a dictionary. We kind of reselect the token that provides the biggest change in the gradient, and this is what we can calculate because okay, we have this calling, and for this calling we can calculate partial derivatives. So we again find the guy that changes the score most, but somehow managed to do in a discrete space. And in this case, okay, we need additional things to make it work and to keep the semantics of a sentence. For example, we can say that if we change one word to another, we don't look for all words in the dictionary. We use only words that are close in the embedding word, and the cosine similarity between them in the embedding for the embedding is higher than 0.8. And also we consider that these two words should be the same part of speech. And for example, we disallow replacement of stop words, and so on and so on. And what we can do now, okay, after applying all the heuristic, it kind of works. And we can see that in this case, we should use two-step approach. At first step, you kind of propose a general way based on gradients, but for replacement of only one token. And at the second step, you use this additional heuristics to make it work and for a sentence to look naturally. Okay, this is the first guy here. And okay, let's ask you a question. Do you understand everything now? And please write a plus sign if you understand what's going on. Maybe not like to every detail, but the general idea of Hotlink. Or maybe we should go into more details here. Colleagues. Okay, I hope okay, so it was not useless. Someone understand what I'm talking about. Okay, very good. Okay, I suggest you to look in the original article and to see what's going on, because okay, it's somehow not very connected to what we'll be talking later. But the general idea is quite simple. Actually. Okay, it's kind of gradient, but for each particular token. And okay, you don't need to go into all these formulas, and especially the notation in the article is not very good. I don't like most of the NPR articles because they try to abuse notation from the very beginning. Okay, it's a different matter. Let's go to a more interesting approaches. It's kind of okay. We don't have a model actually. We try to attack the model, and in this case, we we have a constraint. So it's like we don't can. It's more. You can consider it's more like an optimization problem. So you kind of okay. You can make this two-dimensional space, but you should find optimum of a function not in general space, but for some very strange shaped part of the space. And so this is the true four angles figure, and you want to find example that lies here. And this is basically this semantic constraints. They're pretty natural, and maybe the only way to control is the result. And this help us to avoid some very confusing adversarial sequences that doesn't look like similar in meaning to initial values. Instead, different in many ways. Okay, I will show some example of what Flip is usually doing later. Also, we can try to do this adversarial attacks in a clever way, and we can say that now we, instead of working with this token level, changing of tokens, instead we try to generate an adversarial sequence by slight modification of our initial sequence. And okay, maybe it would be better to go to the next example, and because these figures are nicer. So what we are doing basically, we train the generator G that inputs this original text and outputs adversarial text. And for this adversarial text, it has two requirements. At first, it should has different label than the target model. So it kind of be adversarial this way. This is like the first our requirement. So we have this like it fools the model. And also we have this additional discriminators. And discriminators, okay, one of them tries to see if this adversarial text is looking unnatural or doesn't look like the sequence from initial class. And so we, okay, maybe it's kind of close to gain ideas. When we train these two separate guys, and in the end, we have a generator G that generates adversarial text in terms of that we can distinguish them from initial sequence in terms of semantics because of the discriminators. And also it fools the target model. Here is like, what does it look internally? Here you can see that it's like a variant of variational autoencoder. And after application of decoder, we have this adversarial text in the end. And so we can pass the gradients in this backpropagation through time for GRO, encoder, GRO encoder, and so on. The usual stuff I suppose are familiar with from our previous lectures. And so this is kind of a good attack scheme. Actually, it should work, but when my students try to, okay, not my students actually, but like guys who are participating in a similar course during spring, they tried to implement the article. It just doesn't work. I suppose it's because this variational encoder training and on top of the training of this gun-based architectures are challenging, and we should be very careful with hyperparameters used here. So basically, okay, it's kind of was not very good for me and for my students that try to implement them. But okay, I know that some similar modification work because we developed it. And this is what I did with my colleagues Ivan Fursov, Nikita Krishnikov, Andrei Kravchenko, and Evgeny Vornaev. Idea is similar, but we use clever models to apply. And we say that we try to modify this guy. Okay, so imagine you have a sequence-to-sequence architecture in the very beginning. So, but okay, we have some input. We apply some masking, like in masking language models. So we say that we replace some tokens with mask, and we try to encode and then decode this sequence to get the sequence that is close to the initial one, despite some token being masked. So we have the sequence-to-sequence architecture with this zero recurrent style of encoder and decoder, but we train it as a masked language model and try to recover these missing tokens. So in the middle of this architecture, we have embedded space, and in this embedded space, we have representation of the initial sequence. So we kind of maps initial sequence to this embedding, and we can use, for example, this embedding for some downstream task or whatever. And so we can try to do adversarial attack in this embedded space. We say that we slightly modified this input here, and now we have a different Z prime. And if we use this gradient-based approach, because we can take gradients in the space of embeddings, this is a continuous usual Euclidean space, so we can do it. And after applying a decoder to this modified sequence Z prime, we have a sequence that is close to the initial one, and also it is adversarial because what we are doing is trying to make the model scores as low as possible. In this particular case, we used kind of black box approach, but we trained a substitute model to assess the scores of this Z prime and to find the best direction. Okay, as you can see here is the main steps listed. So if we have this adversarial attack, we start with embedding of initial sequence to embedding space, then we modify it. So now the Z prime is adversarial, then we decode it, and according to the requirements of the model and the loss function we introduced, our new sequence is close to initial one in semantics because we trained a good language model, but is different in terms of classifier score. So this is the base plan from 3 steps. And for step 2, we can try different options. For example, we can try to move in different directions, then try to decode new Z primes for all of these directions, and in the end, like select the best one, or maybe we can do in a more clever way. For example, we define a loss function and optimize it. So it is, and I hope, okay, I will also have some feeling that maybe it's not maybe the simplest approach to create an external example. So, okay, again, a question to you. Do you understand what's going on in this cascade adversarial attack? Please write plus sign if you understand. If not, let's try to deep dive and maybe, okay, discuss some issues and some parts of it. Actually, this model also is not perfect, and I was a bit disappointed when we get the final result because, okay, the metrics was not the best, despite that approach seems very natural and so on. So in the end, we're thinking about what we can try to do to make the approach work and how can we use these last inventions in natural language processing world and how can we use, for example, transformers in a differentiable way. So we came up with a different solution, which we named DILMA, Differentiable Language Model Attack. Actually, some other teams from all over the world are trying to do something like this. And okay, if you want some links, I can provide them. But whatever. The idea is that we have the same model statement. So we say that we have black box attack, but we have this model we can use to obtain, for example, derivatives. Also, we here consider not targeted attacks, so we don't think that we should change a class to a particular different one, but instead we try to change it to something that's different from what we have now. And we have like a number of components to make all this work, and we will review these components in the later slides. Okay, at first, okay, yeah, maybe it's the best step to start. So we train a transformer, again, a language model that is learned to copy sequence in a way I described for Cascada. So we kind of learn model to for a masked sequence to output sequence very close to initial sequence that's not masked. So we reconstruct missing tokens. So kind of okay, we mask x2, but after application of transformer, we get this x2, this close to equals to initial one. So this is the first model we trained. Now we want to modify this transformer. So now it produces not only good examples that are similar to initial one, but that they are adversarial. So in addition to that they're close, they also false. And so what we are doing, we introduce a loss function that has 2 terms. The first term is about that we want to decrease the score of the classifier the attack or substitute classifier. It's like surrogate classifier part. And in this case, we usual requirement similar to what we see in image recognition. We want to make the score as low as possible by taking the derivatives. And the second part is about that our x prime should be close to x. So we have x prime close to x. And in this work, we used the Levenstein distance, or that's also known as edit distance. So we write down all the tokens one by one and find number of changes we should do to our initial sequence. Okay, to create a sequence that is similar to. So the number of steps, the number of changes, what we should do, including new token, deleting a token, or replacing. Actually, no, it's very fast approach. Okay, I was also a bit surprised about it, but it's okay. It's okay in terms of time. Maybe if we have like very large transformers with billions of parameters, maybe it can be not as good, but okay, in my case, it was okay. Okay, so we have this edit distance part. And also we want to have the derivatives. And to get the derivatives, we use this straight through Gumbel estimator. It's a tool to make our language model differentiable. And in this case, we can backpropagate this loss function through these layers here and say how we want to modify the transformer. So now it produces now it produces adversarial examples. And we actually did this modification for each sequence in a row. So we kind of modify each sequence here, or modify transformer for each sequence. So we modify a transformer to full the particular sequence here. And this is what works, because general training of transformer somehow did not work, and we found that this guy was actually a way to increase our scores. And actually, a project we have for one of the team is try to train a general transformer to produce adversarial examples, so we don't need to retrain it for each particular instance. Okay, two notes I want to emphasize. The first one is that as we want, for BERT, I will talk what to do. Let's skip it. For a distance between two sequences, we use not edit distance because it's not a differentiable distance. Instead, we use a so-called deep Levenstein or deep edit distance. We use an encoder to produce representations of a sequence X and a sequence Y, which we want to calculate the distance between. And then for this encoding here of X and Y, we pass them through another fully connected layer, or we can just use like a Euclidean distance here. And then we produce this differential distance. And as everything here is differentiable, encoder and full connect layer, we have like a distance that is close to embedding to edit or Levenstein distance, but is differentiable. So now we can take the derivatives with respect to the distance and can say our model in what directions modify the parameters to keep the edit distance or approximation of a distance low. And another important trick we need to use to get everything differentiable is Gumbel softmax trick. This is the formula that gives us logits we are interested in and what we sample from. And if we have theta that goes to 0, we have usual Rmax decoding part of our language model. So in this case, we just take the probability as a token that has the maximum probability. So we have write down all the tokens PI1, PIG, and select the max value of PIK and get the decoding. It's not a differentiable approach. Instead, we use this soft max approach instead of argmax. We selected some reasonable tau here, and so now we can propagate derivatives for numerous of points. I recommend you to get into more details here in this article, because it's quite useful trick and many guys out there use it for different applications, trying to make things differentiable. And so we have this Gumbers of max to make everything differentiable. And finally, we can run the attack and train it to generate adversarial sequences. We tried to run this attack for 7 data sets, and asymmetric of quality. We use normalized accuracy drop. In this case, what we are doing, we say that if we don't have this web error rate part, we just calculate percentage of examples that we broke. So now the classifier output for initial X and modified adversarial X is different, but also we normalize by error rate. So now we say that we have kind of measure the number, the mean accuracy drop due to change of one token in one sequence. Also, we from the very beginning were interested in how these attacks are good for to resist to defense, and we used these two common strategies for defense to counter our attack and other attacks, adversarial training and adversarial example detection. So adversarial training, we add sequences generated by adversarial attack to our training sample and retrain it. For adversarial example detection, we use as separate detectors that try to identify if this particular example is adversarial or not. So we use these two guys here, and maybe let's start from adversarial detection, and we can see that our approach is close to performance to the approach when you just sample sequences from a language model. And so in this case, we look at ROC-AUG scores for different approaches. So this is, for example, AG dataset from NLP Word. And we see that we have ROC-AUG for this 0.96 for distinguishing between adversarial and normal sequences here. So we can identify almost all of them for hot flip 2. If we use like random sampling, it's very close to like 0.5. And we have something similar when we working with this Dilma to generate adversarial 0.66. I consider it's not very high ROC-AUG, so it's very hard to distinguish our sequences, our adversarial sequences, yes, and initial sequences. So we kind of better at resistance from adversarial detection. And also we can say that for adversarial training, the station is similar. So we can see this NAS scores that we want to maximize as a measure of success of our attacks. And we can see that before adversarial training, hot flip works quite well, and often top 2 is not our approach, but something like FGSM. But after adversarial training, there is no longer the case, and so we have like the best adversarial attack, Dilma, with the highest NUT scores. So kind of it's very important to think about adversarial defense and to measure the quality of adversarial attacks using these defense approaches. You can at this slide compare examples generated by hot flip and Dilma and understand why Dilma works better, and that it keeps semantics better than hot flip, and also hot flip is very greedy and often replace the something to similar words which it considers very topic related, I suppose. And so, okay, we see it here and here and here. And we see that when we compare it to Dilma produces kind of naturally looking adversarial examples here. And I suppose the topic is not that different. So we observe it for NLP data, we observe it for non-NLP data, and what we can further do to improve the state of the art. Okay, let's sum up what we already did. So you see that we can try to construct for NLP models and general sequential data models adversarial attacks that are quite powerful, and despite being a challenging uh, problem because of this non-differentiability and general discrete nature of the data. And also we can say that we can include, if we have a new language model, for example, if someone invents GPT-4, we use GPT-4 to improve the quality of our models. And also we somehow can defend from this attack, but it's not a good way. It has limited success. And I suppose that, okay, it's not the end of the game. I think we can try to consider what are the most robust models to attack these BERT and GPT-3 models good or not for solution of the problems. Also, it's important to see if we can limit the space of transformation. We talked about this before. And also, I think that we are not in the end of this attack defense game. And I suppose it's something like governed architectures trained in a proper way can provide state-of-the-art attacks and state-of-the-art defenses to these attacks. And also, there are some theoretical research in this area. And I suppose that for language model, we can also try to do some advances in this area too. So I suppose, yeah. Okay, last slide is that now we have a nice library that implements many of state-of-the-art attack, but it doesn't implement for some reason our attack. So, okay, you are free to check this nice library and to use it for your own purposes to attack, okay, some language models to be rich. And also you can try our code too and see what you can do from it and examine what is going on when we are trying to use transformer power to generate adversarial sequences. And so finally at the end, do you have any questions? And okay, maybe if you understand everything, write plus sign. If not, please, okay, think 1 or 2 minutes about some questions. Okay, on Friday, we will have a lecture on distances between the sequences. And I hope it can be quite interesting and quite related to what we're talking now, because we did not dive too much into the semantic similarity between two distances. And interesting question, what kind of distances we can impose and why deep learning is important in this learning of metrics and similarity learning too, at least for now. Okay, thank you everyone. So goodbye. And I will make Rodrigo host and he will announce. Okay.
Yes, hi everyone. So we will have now our seminar. I mean, not now, but we'll do it at 5:30. So we have now about 5 minutes for a break. And then we'll have our seminar where we will review the quizzes that we had last week, as well as a implementation of an RNN from scratch. If you remember, last time we had an RNN implementation by using PyTorch, where we used the basic blocks of PyTorch, and then we look how it will be